Tier 9 reframes the scheduling problem as a quadratic unconstrained binary optimization problem, where constraints are enforced by penalty terms inside an energy function. The quantum approximate optimization algorithm alternates between operators that encode the cost landscape and operators that mix between candidate solutions, aiming to bias measurement toward low-energy schedules. This slide shows penalty terms that enforce key constraints. Each bay assigned to exactly one crane, non-crossing behavior, and crane workload limits. Operationally, penalties are how you make constraint violations expensive. If penalties are calibrated well, low-energy solutions correspond to feasible schedules. This slide shows the quantum state preparation using alternating cost and mixer layers. In plain language, the method repeatedly applies transformations that encourage better schedules while still exploring the space of possible assignments. This slide visualizes the quantum circuit architecture used for the quantum approximate optimization algorithm and highlights performance comparison. The takeaway is conceptual. When hardware improves, quantum circuits may evaluate structured schedules faster than classical exhaustive methods for certain instance families. The example instance is described as 4 cranes and 8 bays, mapped into a 32-qubit circuit. Reported make spans are 92 minutes for the classical integer program, 105 minutes for the genetic algorithm, 118 minutes for the greedy heuristic, and 95 minutes for the quantum approximate optimization algorithm. The claim is that the quantum result is within 3% of optimal and uses about 15% of the integer program time. This code section defines the quantum model, including how assignment variables and penalty terms are encoded. Operationally, focus on how constraints are mapped into penalties, because that mapping determines whether the quantum search returns feasible schedules. This section defines the circuit depth and parameter initialization. Circuit depth is the exploration budget. Greater depth can improve quality but increases computation and sensitivity. This section runs circuit evaluations and collects measurements. Because results are probabilistic, many shots are required to estimate performance reliably. This part defines the classical optimization loop that tunes circuit parameters. Operationally, this hybrid loop is how the system learns parameters that produce low-energy schedules. This section decodes the best measured assignment into a schedule and computes makespan. Decoding is critical. Without consistent decoding, you cannot compare quantum results to classical baselines. This final section reports benchmarking results and comparisons. In practical evaluation, the benchmark must include both makespan and feasibility. A fast but infeasible schedule has no operational value. The practice questions test implementation readiness. You practice building the full mixed integer model and solving a small instance, implementing enhanced longest processing time first and analyzing the gap, and running a genetic algorithm with different crossover rates. You also practice defining reinforcement learning state, action, and reward, designing digital twin data streams and what-if evaluation, designing a multi-agent bidding protocol, and formulating a quadratic unconstrained binary optimization model, including penalty weights. Quay Crane scheduling is a high-impact, constraint-heavy problem. Tier 1 provides the complete baseline model, and Tier 2 provides fast heuristics for operational use. Tier 3 and Tier 4 improve decisions through global search and learning. Tier 5 and Tier 6 integrate system-wide intelligence. Tier 9 offers a roadmap for future quantum acceleration by showing how constraints and objectives can be embedded into an energy-based formulation.